operator from periodic to quasiperiodic potentials.
Okay. Thank you very much for the opportunity to speak here. So, what I'm going to talk about, so let us consider H in Rn. Mostly I will concentrate on the case n equal to 2, but it can be dimension higher than this, but it is a multi-dimensional case. So definitely you're surprised by this L. I will explain later why I want to put L, but I think L is greater or equal than 1. So eventually I'm interested in the case L equal to 1. So what is V here? V is periodic, or then V is limit periodic, or V is quasi-periodic, if I will get to this. And this part of the work is joined with Young-Graham V. And this is with Roman-Sternberg. So I don't want to give a very formal talk today. I will avoid kind of lengthy statement of theorems, but I just want to explain how did it happen with us that we started with some kind of perturbation method for periodic potentials, and when L is high, then these periodic methods are very simple. In fact, they are getting more difficult when L is equal to 1, and then we are moving closer and closer to to KM method. So here we have KM method. Here we eventually go to some kind of, it is a type of KM method for quasi-periodic we need something what I would call multi-scale analysis in the space of momenta. So, and I would like to explain what is the character of the difficulties and how the whole field develops, starting from more simple situation and when we move to more difficult situations. So let us start with periodic case. So, and then for periodic case, we are lucky to have Bloch representation theorem. So basically, we replace H by a family of operators HT, and each HT is described by the same differential expression, but we consider a box of the period, say A1, A2, and here we have quasi-periodic condition. U of A1 x2 is EIT1 U of 0 x2, and then the similar thing for derivative and the analogous condition in another direction. And then the spectrum of this operator is already discrete, a union of eigenvalues. And the good thing that the spectrum of the whole operator is the union of spectrum of H of t when t belongs to K, which is reciprocal lattice 2 pi over A1 over A2, this size, 2 pi over A1, this size. So t is running here. And because this is discrete, this gives us a band structure of the spectrum. What? No, what it depends. Okay, you're right. In this case, it should be A1. Okay, now, so let us suppose now we have a discrete spectrum for h of t, and we know that if potential v is equal to 0, then the eigenvalues corresponding to a fixed t, lambda n0 of t, it's convenient to enumerate them by d-dimensional index. Suppose we are in Rd here. So this will be the spectrum will be the collection of points t plus 2 pi m, the length of this vector in power 2a. So, and we have to take union over all m in z d. So then the corresponding eigenfunctions are plane wave, where the impulse is exactly this vector. Okay, here I think that A1, A2 are just 1. So now we know that when dimension is 1, then at the high energy region, these points, they are located further and further away from each other. Yeah? Okay, they can go in pairs, but anyway. So what happens in multidimensional case? I just want to give you simple considerations which helps to understand. Suppose we have a d-dimensional case, and let us consider the spectrum, and let us consider a part of the spectrum which is between 2 points, lambda 0 prime. It can be a big distance. Let us assume this is k0 to L, and this is just 2k0 to L, where k0 is sufficiently large. Let us consider all these points which are inside this interval. What does it mean that this point inside this interval? This means that this vector itself. So if you write t plus 2 pi m 2L between 2k0 to L and here k0 to L, this means that this vector is in fact in a spherical shell. This radius is k0, this radius is 2k0. So this, all this t plus 2 pi m, they are sitting, okay, this is a lattice, they are sitting inside a spherical shell. How many of these points is there? We have to compute the volume. The volume will be something like ck0d dimension, yeah? And if we want to compute the average distance, we have to take the length of this interval and divide by the number of points. So the average distance will be the length of the interval is something 3, okay, something like c k to L, this is some power of 2 or whatever, yeah, k0, sorry, divided by k0d, the number of points in the interval. The average distance is k0 to L minus vc. You can easily check, take L equal to 1, d equal to 1, you will get 1. The average distance for one-dimensional case is really something like k0. If we take L equal to 1, d equal to 2, the Schrödinger operator on the plane, the average distance is of order of a constant, which is just defined by the period of the lattice. If L is 1, d free, three-dimensional case, the average distance for energies of order k0 squared is 1 over k0. So this means that eigenvalues are really getting denser and denser when dimensions goes up. But on the other hand, if it happens that L also is high, then the situation is getting simpler. This is why I often like studying any problem, periodic, limit periodic, quasi-periodic from high L, because this way the difficulties are separated. First you take care about one class of difficulties, then you send L down and start taking care about other class of difficulties. So now, suppose we want to add a potential. So we want to add a potential, and here we have all these points t plus 2 pi L squared, 2L. So there are a lot of them. And let us choose one, which is our favorite one, and we want to consider all such t's that there is an eigenvalue with a fixed energy. So let us find, let us denote S0 of k is the set of t such that there is j such that t plus 2 pi j squared is equal to some fixed k 0 to L. So then it's easy to see that for every j, this is a part of a sphere of radius k0, but they all have different centrums. So you have to consider T in elementary cell. So the P's corresponding to every j will be a part of the sphere. And eventually you will get some kind of a sphere packed into a bag. Yeah? To get this surface, you start with a circle, you take reciprocal lattice, you take all these different pieces and then shift them in one piece. So then you may say, so what is the correspondence between these points and these points? Okay, clearly if you have pj, if you have t plus 2 pi j, it is k, because it is on the sphere. But on the other hand, if you are somewhere away from self-intersection, somewhere here, then then there is one-to-one correspondence between t, j, and some points on the sphere, except some self-intersection points. So you can say except some points, there is one-to-one correspondence between these two pictures. What is so special about these points? Why do I need this picture at all? Because it helps us to understand what happened, what are the difficulties in constructing perturbation theory. When we are in this self-intersection, then we have that there is 2 pi j t 2L equal to some 2 pi t plus 2 pi q to L, where j is not equal to q, because each piece corresponds to some fixed t or q. What does it mean? This means that eigenvalues of a free operator are degenerated for this t. If you consider h0 of t, say, and look at this as a operator with the period 1, then when t is in this point, this means that you have two eigenvalues both equal to k in power 2a. Is it bad? Sure, for perturbation theory it's bad. This means that if t belong to this quasi-intersection, there is very little hope to construct any kind of perturbation theory. So then we say, let us take away some pieces of this self-intersection. Then, what does it mean? If we are sufficiently far away from these pieces, we can hope, at least we can hope, that the distance from one eigenvalue to another eigenvalue is sufficiently large. You see that sufficiently large have different sense in different dimensions, and if we have case 2L greater than D, the simplest possible case, when the distance between eigenvalues in general is big, then if we are sufficiently far from this self-intersection, then this distance can be made sufficiently big, and then the norm of the potential which we want to switch will be much less than the distance between eigenvalues. And then if we are in a situation like this, if we know that they are somewhat spread, we can just construct regular perturbation series. Perturbations, we can take a contour around this. This is a spectral plane, and we construct perturbation series for the resolvent of the operator H0 plus V with respect to H0, and we are happy. But this way works only when 2L greater than D. Because if 2L less than D, then in principle the eigenvalues are located so close that there is no hope to write anything just as a regular perturbation series. What do you do in this case? In this case, let me explain a little bit what we can do. First, let us write the matrix of operator H of T. It look on the main diagonal, you will have something like Pj2LT. So here something like PM2L. Let us write PM2L of T. And here we will have Fourier coefficient, something like V, J minus M. Or if V is a trigonometric polynomial, this can happen just to be 0. Okay? So why do I write this matrix? I want to explain that there is some relationships between every Pj and Pm. Suppose we have Pj which is close to some Pm to A. Let us forget about the rest of the matrix and consider only 2 by 2 matrix corresponding to this J and M. Okay? Then here, if J minus M is not really large, but in whatever sense, I think that my potential is a trigonometric polynomial, then we will have a Fourier coefficient here, non-zero Fourier coefficient. Q is J minus M. Think about 2 by 2 matrix. If this coefficient is not 0, and this one happens to be very close, this coefficient will push these 2 eigenvalues apart. It will change eigenvectors significantly. So this means that if these 2 eigenvalues happen to be close, but in addition G minus M is not large, it's no good. Probably we cannot write perturbation series. On the other hand, if J minus M is large and this is close to 0, then we may say they almost do not interact. They do interact through the rest of the matrix, but we may say they do not interact directly. So this means that in some sense they can be very close and still do not influence each other a lot. So now, because we cannot hope to make all eigenvalues far away from each other, we can hope on such arrangement. This one, which is equal to k2l, is fixed, sitting here. And all others, such that g minus m is not large, they are sufficiently far away. Yeah? But those who are close have m such that g minus m is large. So the game goes like this. If the interaction is strong, we want eigenvalues to sit far away. If the interaction is slow, is very weak, okay, they can sit pretty close to each other. What will it give to us? It will give to us that even if we have a pretty dense spectrum, if we can find such T that interaction is that corresponding, that, okay, I forgot to say what is Pj. This is notation, I'm sorry. T plus 2 pi j. 2a. So we say that if the difference of g minus m is small and the interaction is large, we want corresponding numbers like this to be far away. And when they are close, we want the interaction to be weak. What does it mean in terms of this picture? In terms of this picture, so we have to cut away not only the self-intersection, we have to cut away a more subtle set. And this is where the most of bloodshed is happening. So I just want to say that this multidimensional periodic problem, there were a very good group of people working on this for a long time, and I want just to mention the first paper in this respect. This was Popov-Treganov paper, early 70s, and it was devoted to the case n equal to 2, and they proved the Bethe-Sommerfeld conjecture that if dimension, say, is 2, then the spectrum of the operator contain a semi-axis. And this is a problem, in fact, very closely related to perturbation of Bloch eigenvalues. And the last paper was Parnovsky-Sobolev in 2010, where they prove this Bethe-Sommerfeld conjecture for all dimensions. It was the last nail in the coffin of the Bethe-Sommerfeld conjecture. So. And okay, I maybe have to say a few words here. You know that it's definitely not true for dimension equal to 1. You know that periodic problem has infinitely many gaps for dimension equal to 1. Why is it not true for dimension equal to 2? Because the spectrum of multidimensional Laplacian is pretty thick. So when you switch the perturbation destroy partially this spectrum, but it is not strong enough to destroy it completely. So returning to this picture, what I would like to say something more. So suppose we are lucky and we manage to start with this surface, And we deleted some bad t's here where the perturbation series do not converge. And we are left with a good non-resonance set where perturbation series converge. So it turns out that this, look, the area of this whole surface, multi-piece surface, is the same as the area of the sphere. And when we, suppose we deleted some pieces here, and then we can unfold this again, and what we will get when we unfold this sphere, some kind of sphere with some holes. And it is not so simple problem to describe where they are, but we know that there is such a surface, and when k0 goes to infinity, the measure of the surface, the fraction of the measure of the surface to the area of the whole sphere goes to 1. So it's still quite a lot left. So then, if k happen to belong to this surface, it turns out that we can construct perturbation series for an eigenvalue here plus. We can write complete series, but I don't want to do this now. Also, we can say that the corresponding eigenfunctions turned out to be close to the plane wave. Here, let us put the same gamma. We always can make them the same. What does it mean? This means, and we can do this for any k, and also we can differentiate it with respect to k. Will be 2k plus O of k minus gamma 1. So what does it mean? That we can use implicit function theorem, and we can construct the surface which correspond to a fixed energy, and it will be slightly distorted sphere with some holes. Yeah? If we return to our initial picture in a box, we will have some of these pieces will survive, but there are some regions where we don't know what is happening. For example, here. So here, God knows what happened. So, and this immediately gives the Bethe-Sommerfeld conjecture, because if you can show that the set of k such that this equation holds is not empty, it immediately means that under 0 is a point of the spectrum. And where you are in dimension higher than 1, it is not like just it is not empty, it is in fact a pretty big set, and it looks like a sphere with some holes, but these holes are not big comparing with the whole sphere. Why does not it work in one dimension? Because in one dimension, a sphere is just 2 points. Once you decide to make holes in 2 points, you are usually left with nothing, and this is how you get a gap in the spectrum. So, and this is more or less all what I wanted to tell about periodic potential. But now, what happens if we try to consider limit periodic? What do I do? What do I mean with limit periodic potential? Let me erase it here. So limit periodic, let us again 2L L plus V, and V will be a sum of Vi I from 1 to infinity. And each of them is periodic, but the periods are doubling. So Vi has a period, maybe J here is better. So it has a period 2 in power J. So, but the norms of this potential decay very fast, super exponentially. I will tell you later why it is important, and dimension here is 2. So you may think, what a big deal, I add smaller and smaller potential, so that should be simple. But the perturbation is not only about the norm. You see, this potential is not periodic anymore. This potential has a property that it can be approximated uniformly in X by periodic potential, but it is not periodic itself. So you may think this is the simplest non-local deviation from a periodic potential. And non-local, this is a very bad word, as you probably all know, because this means that perturbation theory is not going to be sweet. So now let us make some agreement. This is something like V1 plus V2 plus V1000 plus blah, blah, blah. And I want to somehow in some way, I want to form some groups of them. I don't write any formulas, but then the period of this will be something like 2 in power 1000, and here it will be even bigger, but then the norms of this will decay very fast. So I want to form in such a group that the norm of group, I mean not in the algebraic sense. I mean that let us assume that we write this as a sum of the potential Vj in such a way that Vj decays very fast. Okay, it's maybe not, it's pure technical remark. If you don't care, forget about this. But let me explain what is the main difficulty if we try to treat this case like that, like a periodic case. Let us consider a relatively simple problem. Assume that we still have a periodic case, and our period is A1. Then, when we put our sphere into a box, then the size of this box 2 pi over A1. This is A2, this is 2 pi over A1. But if the potential has a period A, it definitely has a period 2A, 3A, 4A. Suppose I'm not good and I think about the same operator, but I think that it has a period 2A1. What happens with this picture? You see, if for A1 the picture is in this box, in a bigger box, yeah, then for 2A1 it should be in a smaller box, but they should be somehow related. How do I do this? I have to cut it by 4 parts, by 2. Then I move all of this stuff together in a parallel manner. Imagine you cut this with scissors, and then you move it in one box, and you again get the same sphere, but packed already in a smaller box. What happened here? It happened you have much more self-intersections, yeah? if you also want to delete some neighborhoods of this self-intersection, you're getting what? A mess, complete mess. And if you consider a higher and higher period, then the box is getting smaller and smaller. And then if you want basically to make the same perturbation, yeah, here it's maybe relatively simple. If you go here, it's become very difficult. And this is a problem, one of the problems with adding one potential after another. You want to, this has some period 2 and 1, this has a period 2 and 2. So suppose we solve this problem. Yeah, this is in the box 2 pi over 2 and 1. Suppose we were lucky and we managed to delete all this self-intersection and everything else what we need. Then what's that happening here? Here we don't know what happened, but we don't care too much because this region is big. Now, if we want to add W2, which has a bigger period, yes? First, we have to think about H plus W1 as having a bigger period before we can add W2, because W2 has bigger period than W1. So before we can add W2, we have to put this stuff in a smaller box. So what do we have? We have a mess, yeah? So, and even if we, but then we can say, okay, we have a mess, but if W2 is very small, maybe, you see, maybe we can still survive. We have a smaller box, but then we take smaller and smaller pieces. Maybe we will be fine. No, we won't. Why? Because here we have these regions, relatively small regions, where nobody knows what happens. Yeah? And then once you start cutting and folding it together, these bad regions, which are small, suppose we have very little information what is happening here. When you move this stuff together, these regions which were so small and modest on this picture, all of a sudden start feeling by themselves a smaller picture. So it is like you cannot really to understand what happens for limit periodic potential, you have to understand at every step not only what is happening in good regions, and we have a good machinery to understand it, but we also have to understand what is happening in bad regions. Here we do not have nice formulas. So they just, this is like bad guys kind of start attacking good, peaceful guys after you know, because you mix all of them together. In this picture, both non-resonance, nice regions and bad regions, they all start living together, then there is no way to understand what is happening. So it looks that as an absolute mess, and what is the way out of this mess? Okay, one more difficulty. You want, this is described by a certain dispersive equation, 0. If you want to take out, your purpose is to find some region which corresponds to lambda changing between lambda plus delta lambda. What will be the size of this region? This is T. It will be something dt. The size of the region, it will be something like d lambda divided by d prime. But the problem is that d prime, not only d prime is 0, there are 1 million of other derivatives which cannot be 0. So even if you want to delete a very small region in terms of lambda, you really cannot estimate the size of the region in terms of t. So, and as I just said, it turns out that the way to get out of this mess is to, in fact, to stop thinking in terms of real variables and start thinking in terms of complex variables. So how do we think in terms of complex variables? So this is the part where dimension, it's important for me that dimension is 2 and not higher. So let us again consider V equal to 0. Consider K 0, a circle, and describe every point on the circle like K0 nu, where nu is cosine phi sine phi. So then we are in trouble with our perturbation theory for points which satisfy, if the period is 1, to such conditions. So assume that L to L. So if we have such condition, then it corresponds to this self-intersection. Now, what does it mean for phi? This is in fact an equation for phi. This means that these two disks can intersect, and if they really intersect, there is a real phi which satisfies to this equation. Their K is K0 nu. This means that all such, in fact, there are two such phis, phi n and here minus phi n, and if we change n, we got a lot of phis. But this is when these two circles can intersect. What if n is such that in fact they don't intersect? We are still trying to solve this equation, and we will get a solution, but it will be not a real one. If we have two disks which almost touch to each other but do not intersect, we call this quasi-intersection, we will have two solutions of this equation which are very close to real axes. So this kind of reduces, you see, it's very primitive, but it's very important. It reduces geometry to complex analysis. If these two disks intersect each other, you have a real root. If they're extremely close but still do not intersect, you have a complex root but very close to a real root. Now, considering like this, I say, let us exclude this self-intersection. In this language, this means that I'll take every root and I delete some neighborhood of it. I don't want to tell you anything about the neighborhood of the size of the neighborhood. It's all calculation. But it is small enough that we have quite a bit of left. It is not even up to scale. We have a lot of space left on the interval 0 to pi. On the other hand, this neighborhood is big enough such that, remember, this is the plane of phi. And if we are outside of this neighborhood, then we can say that outside of this neighborhood, k squared minus k plus 2 pi n, 2l here is greater than some k delta, which is much greater than v. What does it mean? This means that if we have complex k, complex phi, lying on such neighborhood, then the perturbation series, in some sense, the perturbation series for operator H0 plus V is converged with respect to H0. In some sense, we can, I don't want to go into details, we can construct perturbation series on the disk around each root. It's not still clear what it is good for, but I will explain you further what it is good for. I only say to you now that if phi is not in this disk, suppose phi is somewhere here. So this, we say phi is not in a resonance set. Then there is, and phi is real. There is an eigenvalue of the operator H minus delta plus W1, and this eigenvalue of K nu correspond to phi, is close to K squared. We can differentiate this. And the corresponding eigenfunctions plus also something small. Now, the main thing that we want to add W2. So, but before we add W2, let us think about W1 as having a period which is, say, twice bigger than initial period. Or not, or let us say we have period A1, A2, and now we have period NA1 and A2. Then we can use discrete version of the Bloch theorem. The spectrum of the operator H1 corresponding to this period and H1 tilde corresponding to this period will be lambda of H1 tilde will be the union of lambda of H, let me say lambda S belongs from to 0 and the dimension D, and lambda S is the spectrum of the operator H, and here, if here we had T, then here we will have T plus 2 pi S n. So now let us lambda. This is a spectrum of this operator. So what does it mean? That the spectrum of an operator with bigger period will be the union of the spectrums of the operator with smaller period, but we have to take different quasi-momenta. Let us fix S, and let us think about this operator. Then, in fact, we can, when S is not 0, first we can do with this operator, it has also pretty small period, the same picture as before. So first, this was our initial disk. Now for a fixed S, not 0, we have to construct similar disk, maybe somewhat smaller. Okay, and then our resolvent, so this is the centrum of the disk, our resolvent of the operator H, C plus 2 pi S n minus K squared minus 1 converges on the boundary of each this disk, and using Rouché's theorem for the determinant, they can in fact interlap. We can say that the resolvent of the perturbed operator have the same number of poles inside each connected. So if we had here 2 poles, then we will still have two poles for this perturbed resolvent. Now, what we can do here, in fact, we can now squeeze this whole contour around these new poles, and we can make a smaller set around them. We cannot squeeze this around initial poles. It would be too rough. But we squeeze it around new poles, and we will get t plus 2 pi s over n minus k squared minus 1. And here we can control it by some, this is the ratio of the big radius to the small radius in power the number of poles inside. So when we took much smaller neighborhood of these poles, our estimate for the resolvent got worse, but we still can control it. Why do we want to squeeze this stuff? Because we have a lot of S. We cannot keep it the same size, because then they will start overlapping and we will have nothing left. So what we did, the picture goes like this. This is the circles in the first step. Then we make small disk, delete small disk for every S on the second step. And every disk is much smaller, but there are more of them. But we balance our parameters in such a way that still there are a lot of phi's which do not belong to any of these circles. And for each of these phi's which are here, we can write that we can add potential W2, and then the top eigenvalue will be close to W1 plus something really very small. We can differentiate it and the eigenfunction will be close to two eigenfunctions for the first step. Now, what does it mean for our distorted circle? So this is the set of phi outside these holes where we can say something. This is our distorted sphere for the first step. What happened on the second? We delete a lot of small intervals from here, and we perturbed it a little bit. And this is how the picture looks after we switch the perturbation W2. Then we want to switch W3. So what happens? On this picture, we will have even more holes over smaller and smaller radius. Why do we want phi to be complex? Exactly of this, do you remember I told we start with a known pole of unperturbed resolvent. Then we know that the perturbed one has, say, suppose we have two. Also we'll have two poles inside. Then we have to make a contour around these new perturbed poles, and we do this on every step, and eventually we get something like Swiss type structure. Swiss cheese, it starts looking like a Swiss cheese, yeah? Infinitely many holes on good small Swiss. I heard from French people that in United States they don't know really how to do Swiss cheese, that they use some kind of pasteurization, and after this, the holes, you have just a few big holes, but you do not have a real Hunter type structure. So you get a Hunter type. So, and here I want to finish my talk that it's extremely important to act in the complex space of phi, because if you try to act in real space, then you will need to write formulas for all these strongly perturbed eigenvalues. So you have to write formulas which you don't know if you try, and which you probably cannot know if you want to stay in the real space. Once you go to the complex space, you have Rouché's theorem, which takes care about everything. The Rouché's theorem, it does not find you a formula for a new pole, but it says you that some kind of slightly perturbed function still will have the same number of zeros inside certain region. And this is all what you want to know. So now I was supposed to talk about quasiperiodic. I'm not going to, but I will just say you that there is a modification which works for quasiperiodic too, but it's a different construction. Thank you so much.
So just to understand what you know actually proves. So you have these lambdas that are the eigenvalues with these boundary conditions of these. I mean, when
already for almost periodic, you already do not have flat-headed comparison.
Yes, but now you basically you have typically a lambda of t, and what you know when in the case of the Laplacian is that this lambda of t is actually also changes in t, so you get AC spectrum in the band, and not like an eigenvalue with infinite multiplicity. And so this is basically what you prove now, but you have to sort of make your set of momenta smaller and smaller, but you somehow know there is still some AC spectrum.
Yeah, it is. We even can prove that it has a lot of holes, but in fact it's not so small. It's in fact still pretty. So the basic result that if you take a Laplacian, yes, you take and then potential, almost periodic potential destroy this Laplacian, and it make kind of a lot of holes in it. But all after all, a big part of the Laplacian survive, and this means what? We have a big branch of absolutely continuous spectrum. We have beta Zimmerfeld conjecture. The spectrum contains a semi-axis. So we have some other properties of the Laplacian. For example, we have ballistic transport. I did not talk about this. So all this means that kind of there are fees such that for which perturbation formulas do not work, but there are still a lot of them for which perturbation formulas work.
When you apply Rouché's theorem, do you know that the zeros are supposed to remain on the real axis, or can they really wander away?
Yes, they can wander away, and this is a well-known effect. Say, for people who study periodic potential, you know that if you have intersection of isoenergetic surface and you switch the potential, they become quasi-intersection. What does it mean for us? We had a real root, a real pole, we switched the potential, it became slightly complex. Yeah, this is kind of important, that you do not have to think about geometry at all. You may think about all these things in terms of complex analysis and just using Rouché's theory. Okay.
In the multidimensional case, do you use complex analysis of many variables?
No, I don't use. I did only two-dimensional case for almost periodic and limit periodic. There are some problems for multi-dimensional. First, you need more than one angle variable, but there is some additional problem. You need to count, say, the number of lattice points. Let us just think about periodic problem. You need to think about the number of lattice points in a thin region. If dimension is 2, we all know this is about k in power 2/3. Yeah? So this power is less than 1. And it's the estimate like this needed for quasi-periodic 2 But so, shortly speaking, this is not the only problem. Yeah. Okay. So for that we need more than one angle variable is not the only problem. There are some serious geometrical difficulties.
Do you have results for multidimensional cases?
No, for limit periodic and for quasi-periodic, I have only for dimension 2. Maybe 2 is multi-dimensional.
It's a very high dimension already, right?
The difference between multi-dimensional and many-dimensional. Yesterday, difference.
Is the assumption of super exponential decay of the lower harmonics crucial to your method? Because in one-dimensional case it is not.
It's crucial because I told you that I need to know how many poles can concentrate in one exponent. You know, you can have such benches, such many circles stick together. By the way, it doesn't happen in one dimension. In one dimension, you have usually just 2. Then, how I estimate the estimate for the resultant is getting worse and worse when you have a lot of circles which stick together. I use very rough, extremely rough and primitive estimate for the number of circles which can stick together, just very rough. And then, for this roughness, I have to compensate by something, and I compensate by putting very strict requirement on the decay of the series. If I could know that not too many disks can stick together, I could release the condition on the smoothness of the potential.
And still, do you really need super exponential decay or just sufficiently fast exponential?
I think the way how I do this, I need super exponential. I don't say that it cannot be improved, but I require super exponential, and this is, you know, you can reduce smoothness of the potentials to some other things, but this super exponential decay, it's kind of important. At least in how we still can do this.
Any more questions? Well, if not, let's thank Yulia again.